Hi everyone, my name is Anthony and welcome back. So today the problem we have here is a vertical pipe with some liquid, which is in blue here, uh, flowing down the sides of our vertical pipe. And we have some air or some vapor phase flowing in the opposite direction. Now, Sherwin and Gilligan have actually established a relationship between the Sherwood, the Reynolds, and the Schmidt numbers for a problem like this. And I have these ranges down here for the ranges of the Reynolds number and the Schmidt number for which this is usable in. And what we're going to do is we're going to kind of uh, work our way to this. Um, so first we're going to see why the Schmidt number, the Reynolds number, and the Sherwood number are correct for describing this situation. So we're going to be doing some dimensional analysis here. And our first step is going to be to identify what variables are important to the problem. So the first variable that's important to the problem is going to be the mass transfer coefficient, which is our Kc here. And I should have explained at the beginning, we're looking for the mass transfer between the liquid phase and the vapor phase due to evaporation. So that is why this mass transfer coefficient is important. Now, for important variables, we also have the velocity, so how fast everything is moving. We have the kind of the properties of the liquid. So we're going to have the density here, and we're going to have the viscosity. And of course, these would change if we were using like water versus some other, like honey, very different viscosity. Our mass transfer coefficient, or our mass diffusivity between our two phases. And we also have some characteristic length. In this case, for the pipe, it's going to be the diameter of the pipe. But if we had some other shape, it wouldn't be the diameter. It would be whatever characteristic length can be used to describe the geometry. So these are the variables that are going to be important here. Now, what we want to do is we want to kind of use the Buckingham pi method to turn these into dimensionless groups. And the way we're going to do that is we're going to create a matrix here. And we're going to put our our basic units here. So we're going to have kilograms, we have meters, and we have seconds. So we have a mass, a distance, and a time. And what we want to do is we want to go through and we want to write down the powers of every unit as it appears in the variable. So, for example, Kc, the unit for Kc is meters per second. So kilograms does not appear, so that would be 0. Meters has a power of 1, and seconds has a power of -1, because it's on the bottom. So this is the idea we want to use for all of these. Velocity is also meters per second, so it will look the same. Now, density is kilograms per meters cubed. So we have a 1 for kilograms. And then, since we have meters cubed on the bottom, this would give us a -3. Again, seconds does not appear. There's no time, so that would be 0. For viscosity, that's going to be kilograms over meters seconds. So we have -1 for both of these. For our diffusivity, that's going to be meters squared per second. so kilograms does not appear. Meters, and since we have meters squared on top, it's going to be the power of 2 per second as -1. And finally, our characteristic length is only meters. So this is our matrix that we use to describe this problem here, using these variables. Now for the Buckingham pi method, our next step is going to be to take the total number of variables, which in this case is 6, and we're going to subtract the rank of this matrix. And in order to get the rank of the matrix, we're actually going to use Python. And what's up here? I already wrote it out in Python, so what I did here is I put this matrix right into Python. This is the same one that we just made. And then we have a line here that will tell Python to find the matrix of that, or find the rank of this matrix. And of course, you don't have to use Python. This is just probably the easiest way right now. And this gives us a 3. So the rank of our matrix is 3. So our rank is 3. So we're going to take the total number of variables, which is 6, minus the rank, and that's going to give us 3. Now, this number right here, this tells us how many dimensionless groups or dimensionless numbers we can use to completely describe our problem. So what we're going to do is, using these 6 variables, we're going to create 3 dimensionless groups, and we're going to call them pi1, pi2, and pi3. So the way we want to go about doing this is we want to create a core group of variables. And the core group of variables doesn't matter too much. The only real constraint for it is that in our core group of variables, the core group has to have 3 variables in it, because our rank is 3. The rank of our matrix is 3. So our core group is going to contain 3 variables, and each unit has to appear once. So we need at least once. Each unit has to appear somewhere in that core group. So for example, we could choose, if we were to pick 3 variables, maybe our mass transfer coefficient, velocity, and our characteristic length as our core group. This is three variables, which is the number of our rank, so that's okay. But if we look, we see we have seconds that appears once, twice. It doesn't appear in our length. We have meters that appears once, twice, 3 times, but we don't have kilograms appearing at all. So because of that, we actually can't do this. So what I'm going to use for our core group is going to be our diffusivity, our density, and our characteristic length. So this is going to be our core group here. So this is 3 variables, and if we check, it looks like we have, in our density, we have kilograms and meters. In our diffusivity, we have meters and seconds. So just between those two, all of our variables are there, so that's okay. And then our characteristic length only has meters, and that's okay because, again, all of our units appear in there. So once we have our core group, we're going to make 3 new groups, and again, we're going to call them pi1, pi2, pi3. This is going to be our core group. multiplied by one of the variables that we didn't use. So in this case, our mass transfer coefficient. And the way this is going to work is that there are powers that are unknown to us in our core group, and then our non-core group variable is just going to be to the power of 1. And what we're going to do is we're going to determine these powers in order to make this unitless. This expression, we want this expression to be unitless. So what we're going to do is we're going to write down the units. So our diffusivity is meters squared per second. This is all going to be to a power. Our density is kilograms over meters cubed. This is going to be to a power. Our characteristic length is meters, and that's going to be to some power. Then our mass transfer coefficient is going to be meters per second. So we want to choose A, B, and C to make this unitless. So the first thing we want to notice here is that the only place kilograms appears is in this expression raised to the power of B. So in order to make this work, in order to make this unitless, B is going to have to be 0. Because if B were anything else, it couldn't be unitless because there would have to be some other kilogram somewhere to cancel that out, but we don't have another kilograms, so B has to be 0. So we know B is 0. So the next thing we want to look at is this seconds that's on the bottom here. The only other place we have seconds is in this expression raised to the power of A, and we want this seconds to be on the opposite side of this seconds in order for them to cancel. So that tells us that A is going to be to the power of -1. And then finally, we can write an expression here where we have meters raised to the power of 2 times -1, so -2. We have 0 here, so there's no meters here because B is 0. We have some meters raised to the power of C here, and then that should equal this. Did I do that right? Meters. Yeah. So -2 plus, that's not. -2 plus C equals 1, yeah. I think I'm confusing myself here. Here we have 2 meters. We have meters squared on the bottom. Here we have meters on top. And here we have meters on top. So we have 2 meters on the bottom here. We have 1 meter here. So C has to be 1 in order for us to have 2 meters on top and 2 meters on the bottom. So that gives us C equals 1. Okay, there we go. So if we're gonna rewrite this with our units or with our coefficients. So what we end up with is Kc times our characteristic distance all over our diffusivity. Okay. And this number actually has a name. This is the Sherwood number. Okay. So this is pi 1. This is our first dimensionless group, and it is the Sherwood number. So now we're going to do the same thing. So I'm going to rewrite all of this. But instead of using our mass transfer coefficient, we're going to use the next non-core variable that we have, which is velocity. So now we have velocity. And if we, again, go out and write all the units out, meters squared per second, we have kilograms, meters cubed, meters, and actually it turns out velocity is also meters per second. It's the exact same units as our mass transfer coefficient. So we don't even need to do any real work here. We've already done it up here. We know that this is going to be -1, this is going to be 0, and this is going to be 1. Again, that's because the mass transfer coefficient and the velocity have the same units. So in order to make this unitless, we're going to have the same exact coefficients, same exact powers. So the only difference here is that this is going to be velocity times characteristic distance over our diffusivity. And this also has a name. This is the Peclet number. Yes. Okay, so that's our second dimensionless number, Peclet number. And finally, we have our pi 3, which we have our same core group here. But now we have our last variable, which is our viscosity. So we have meters squared over seconds raised to the power of a, kilograms over meters cubed raised to the power of b, and we have meters raised to the power of c. And over here we have kilograms meters seconds. And we're looking for our a, our b, and our c. Okay, so we're going to look at kilograms first, because there's only 2 that appear. And since they're both on the same side, we're going to need to flip this in order to make them cancel. So already we know that b is equal to -1. If we take seconds, we only have 2 seconds that appear. And again, they're both on the same side, so we're going to need to flip this one in order to make them cancel. So a is also -1. And we're going to do the same thing that we did in the first one for the meters. Here we have 1 over meters squared. Here we have meters cubed on top. Here we have meters to some power. And here we have 1 over meters. So it looks like we have 3 meters on the bottom. And 1, 2, 3, and 3 on top. 3 on top plus whatever this is. So this has to be 0. Because this and this already cancel with this. So this, there's nothing that can cancel with that. So that means that C must be 0. Okay, so those are our powers there. And we're going to write this as our viscosity over our density times our diffusivity. And I believe this is the Schmidt number. So this is our third dimensionless number. So what we're left with is 3 dimensionless numbers Sherwood-Peclet-Schmidt number. And what we're actually going to do, we're going to take pi 2 divided by pi 3. So that's that. Write out the units here. So these will cancel, and what we'll be left with is this, and this is the Reynolds number. So we took one dimensionless group, divided it by another dimensionless group, and what we end up with is another dimension, a different dimensionless group, which is the Reynolds number. So these, this one, Sherwood number, Schmidt number, and the Reynolds number are going to be the dimensionless groups that we use to describe our problem. And if we go back up here, look at what Sherwood and Gilligan did. They have the same thing. Sherwood, Reynolds, Schmidt number. Now, the interesting thing about this is that we've condensed a problem of 6 variables into a problem of 3 variables, which makes running experiments a lot easier and a lot more convenient. So if we were to graph these, if we were to run an experiment with these, and we would end up getting data points. Whatever these data points are, it's something. So what we would do is we would use a linear or non-linear regression method to fit some line to this data. And if we were to fit it to the form of Sherwood number equals sum A times the Reynolds number raised to some power times the Schmidt number raised to some power, what we would actually end up with is this up here, is what Sherwood and Gilligan did. So that's actually what we're going to be doing. We're going to kind of simulate an experiment where we're actually gathering this data. We're going to introduce a little bit of error into our experiment because in reality, if you were to do an experiment, of course you would have error. And we're going to see, using linear and nonlinear regression, if we're able to get the same values for A, B, and C as what is listed up here. So we're going to be using Python for that, and we're going to be doing that in the next video. So this is all for the dimensional analysis. We found that the Sherwood, Reynolds number, and Schmidt number can be used to describe our problem, and we're going to find a relationship using linear and nonlinear regression. So I'll see you guys in the next video. Thanks for watching.